Hey everyone, and welcome. Today, we're going to tear down the C programming language to its very foundations. We're going to look at its structure, piece by piece, so you can see exactly what makes it tick. So, have you ever wondered what a computer program really looks like on the inside? Behind the curtain? Well, it's not magic, not at all. Think of it like a super detailed blueprint for a building. And today, we're going to walk through that blueprint together. All right, so here's the game plan. First, we'll look at the blueprint of a program. Then, we'll see how we bring that code to life. After that, we'll cover how you store your information, talk about the unchangeable rules, constants, and finally, we'll get into how you can really control your data types. Okay, first up, the blueprint itself. I mean, you wouldn't just start throwing bricks and wood together to build a house, right? Of course not. And C code is the same. It follows a really specific, logical layout to make sure everything works just the way it's supposed to. So every C program is basically broken down into these 6 key sections. We've got documentation, preprocessor directives, global declarations, function prototypes, the main function, and then the function definitions. We're going to hit every single one of them. All right, let's start at the very top. And what's funny is this first part, it's not even for the computer. Nope, it's for us, the humans. This is your documentation section. It's where you leave little notes to yourself and others. Things like the file name, who wrote it, and most importantly, what the heck the program is supposed to do. Trust me, your future self is going to thank you for this. So will anyone else who has to look at your code. Okay, next up we've got the preprocessor directives. Think of these as the prep work instructions. They're commands that get run before the compiler even starts its main job of translating your code. And the one you'll see all the time is #include. It's basically you telling the compiler, hey, before you do anything else, go grab this standard toolkit. For example, including studio.h gives you all the standard input and output tools, like the super useful printf function. All right, now we're moving into what I like to call the public square of your program. This is the global declaration section, where you put stuff that needs to be visible from absolutely everywhere in your code. This is where you might declare a global variable that every part of your program needs to access. But, and this is a big but, be really careful here. Use this section sparingly. Why? Because having too many global variables floating around can turn your code into a tangled, confusing mess real fast. Next up, function prototypes. The best way to think about this section, it's like a table of contents for all the custom tools or functions that you're going to build in your program. What's so great about this? Well, it tells the compiler, hey, just so you know, a function with this name exists and this is what it needs. You can then write the actual code for that function way down at the bottom of your file. It just gives you a ton of freedom in how you organize things. And now, we've arrived. This is it. The absolute heart, the engine room of every single C program, the main function. You have to get this. No matter if you have 10 lines of code or 10,000, the computer always starts running your program right here, inside main. And when it gets to the end and sees that return 0, that's the signal to the operating system that, hey, we're done and everything went smoothly. Okay, last but not least in our blueprint is the user-defined functions section. If the prototypes were the table of contents, this is the actual workshop where we build all those custom tools we promised we'd make. This is where the real heavy lifting happens. And here's a pro tip. Make sure each function does one thing and does it well. Sticking to that simple idea is the key to writing code that's clean, easy to understand, and way, way easier to fix when something breaks. All right, so our blueprint is all laid out. We've written the code, but how does that simple text file actually become a program you can run? Let's dive into that right now. This little flowchart here shows the whole journey. It starts with your source code, that C file you wrote. You feed that into the compiler. The compiler is like a super smart translator that turns your C code into something called object code that the machine can almost understand. Almost. Next, the linker steps in. The linker is like a project manager. It takes your object code and pulls in any other pieces it needs, like code from those libraries we included earlier. It stitches everything together into one neat package, the final executable program. And that's the thing you can actually run. Okay, so every program at its core is all about managing information, right? So let's talk about the containers we use to hold all that data. We call these containers variables. It sounds kind of technical, but really, a variable is just a labeled box in your computer's memory. You give the box a name, you tell the computer what kind of stuff you're going to put in it, and then you're free to store information in there and change it whenever you want. And that kind of stuff has a name. It's the data type. It tells the variable what it's allowed to hold. See, C is very particular. It needs to know, is this box for whole numbers, which we call an int? Is it for decimal numbers, a float, or just a single text character, a char? These are the basic building blocks, and from them, we can create all sorts of more complex data types. But hang on, what if you have a value that should never change? You know, like the value of pi, or maybe the maximum number of players in a game. For those, we need something special. We need constants. And in C, you've got two main ways to create these unchangeable values. There's the old school way, using #define, and then there's the more modern approach with the const keyword. They both get you a constant, but how they work under the hood is totally different. Okay, check this out, because this is where it gets really interesting. Define is basically a simple find and replace tool. It happens before the compiler even sees the code. So if you define something like 2 as 1 plus 1, and then later you write code like result equals 2 times 2, you'd think the answer is 4, right? Wrong. The preprocessor just replaces 2 with 1 plus 1. So your code becomes 2 times 1 plus 1, and order of operations says that's 3. Whoa. Const, on the other hand, creates a proper, real variable that the compiler knows about. It has a type, it follows the rules of scope, and it prevents those kinds of nasty, subtle bugs. That's exactly why const is almost always the better choice in modern C. All right, let's zoom in on the final details now. One of the coolest things about C is the amount of control it gives you over your data. You can really fine-tune exactly how it's stored. We do this with things called type modifiers. So you can take a basic integer, an int, and add the modifier short to make it use less memory. Or if you need to store a gigantic number, you can use long. You can even tell the compiler that a number will never be negative by using unsigned. What that does is it lets you use the bit that was for the minus sign to store more positive numbers, basically doubling your maximum positive value. Pretty cool, huh? Now, when you want to actually display one of your variables, you can't just throw it at the printf function. You have to tell printf what kind of data to expect. That's where format specifiers come in. You use %d for a standard integer, %f for a float, %c for a character, and so on. And you have to get this right. If you tell it to print an integer but give it a float, you're going to get garbage on the screen. So, what if you want to know exactly how much memory a certain data type is using on your machine? Well, there's a super handy tool for that called the sizeof operator. It'll tell you the size in bytes, but here's the catch. It has a little quirk. The number it gives you back isn't a regular int. It's a special, unsigned type called size_t. And since it returns this special size_t type, you need to use a special format specifier when you want to print it. This is the right way to do it. You use %zu. Think of the z as standing for size_t and the u reminding you that it's unsigned. That's the combo that tells printf exactly what kind of data it's about to get. Now, here's the mistake a lot of people make. They just use %d, the one for a regular integer. And you know what? It might seem to work on your computer. But the problem is, on a different computer or a 64-bit system, size_t might be way bigger than a standard int. That can lead to compiler warnings, or even worse, it could just print the wrong number without telling you anything's wrong. So the bottom line is simple. Always use %zu to print the result of sizeof. It's the only way to be sure. And there you have it. That's the complete anatomy of a C program, all the way from the high-level blueprint down to the nitty-gritty of managing memory. You've got the foundation, you've got the tools. The only question left is, what are you going to build first?